Okay, today we are going to discuss about Bohr models for hydrogen atom. So before going, in our previous videos we have discussed about Rutherford nuclear model of atom. So Rutherford he gave a good model, but he could not explain the stability of atom. Okay, so he considered electrons to be a charged particle, and then since it is a charged particle, it will after some time it will dissipate some energy, it will give out, emit some energy, and then what will happen is it will collide, okay, with the nucleus. Okay, so he could not account for the stability of atom. So this Bohr model for hydrogen, okay, finally we came here. So this Bohr model of hydrogen atom, in this, okay, Bohr was able to account for the stability of atom. Okay, or we can say this model is an improvement of Rutherford's model. Okay, so in this model he used the concept of quantization also. Okay, the concept of quantization. Okay, he used Planck concept, okay, of quantization. So to understand better, let me draw a 2D structure. So through this hydrogen atom, okay, he was able to explain, okay, the stability, okay, and using the concept of quantization. So the electrons, okay, move around the nucleus. Okay, here the electron move around the nucleus, so in a circular path, okay, of fixed radius and energy. Okay, so we call those radius or energy as orbits or stationary states. Okay, these are stationary states or allowed energy states. Okay, they are arranged concentrically around the nucleus. Okay, so let us denote the first shell as or orbits or stationary state as n1, the second one orbits or stationary state as n2, n2, n3, n4. So these orbits have fixed radius and energy. So let us denote those energies E1, E2, E3 and E4. So this is just for get better understanding. So he was able to explain, okay, that these electrons are in a fixed circular orbit. Okay, and then the electrons, okay, here does not, the energy of this electron, okay, in the orbit does not change with times. Okay, so the energy of electron in the orbit does not change with time. However, electron will move from a lower energy state, okay, n is equal to 1, or we call it as the ground state. So an electron, okay, may gain energy or absorb energy or radiation. Okay, after absorbing radiation, what will happen is they will move from this stationary state to higher or stationary state, okay, n1 to n2, okay, after gaining energy. Okay, or they might move from n1 to n3 or n1 to n4, okay, depending on how much energy they absorb. Okay, after absorbing radiation, they will move to higher energy level, okay, n2, or we can say E1 to E2, like that. But after some time, okay, they will dissipate or they will give out radiations or energy, and they will come back to their original position. So after coming back to the original position, okay, they will lose their energy. Okay, so chances are that they may either from n4 to they may either come back to n3 or n2, okay, like that. The frequency of radiation, okay, the frequency of radiation absorbed or emitted when transition occurs between the two stationary states differ in energy by delta E. So the frequency, okay, between two states, okay, E1 and E2, okay, so electron move from E1 to energy state E1 to energy state E2, okay, they absorb energy, and then when after emitting energy they come back to their original position E1, okay. So the difference, okay, in energy, okay, will be given by delta E, okay. So the frequency of radiation given by nu, frequency given by nu, is equal to delta E by h, okay. So delta E, so what will give delta E is E2 minus E1. So E2 minus E1 will give the energy difference, okay, by h. So here E2 and E1, okay, these are the energies, okay, of the E1 is the energy of the lower state, E2 is the energy of the higher state, okay, and h is Planck constant, and this is, you know, nu, okay, frequency. So the angular momentum of electron is quantized, okay. So the distance between this is given by r, okay, radius, and this electron is moving, okay, revolving around the nucleus, okay, with velocity v, okay, and tangent. So this is given by a vector, okay. So an electron moving, okay, moving around the nucleus with radius r and velocity v, okay, is given by mvr, okay, where m is mass, v is velocity, r is radius, okay. This is from the classical mechanical, okay. Classical mechanical point of view, okay, mvr is equal to h by 2 pi. So me is the mass of the electron, okay, v is the velocity, r is the radius, okay, so h by 2 pi, n comes here, okay. So n is an integral number of value, okay, 1 2 3, okay, like that. So this will give the angular momentum of electron, and this value, okay, will depend on the number of n, okay, that means number of shell, okay. So each electron has fixed, okay, angular momentum, and then it is said to be quantized, okay, that means they have fixed value or specific value, okay, quantized means. So after this, okay, some conclusions were drawn out, okay. So those are according to Bohr's theory for hydrogen atom, okay. The stationary state for electron are number s, n is equal to 1 2 3, okay. So n represent the number of shells, okay, or those shells we call it as principal quantum number, okay. So principal quantum number will come later also about this in our next videos also. So these integral numbers are known as principal quantum numbers, okay. The radii of the stationary states are expressed as, okay, the radii of the stationary states, okay, are expressed as Rn n square n naught. R n number of stationary states, okay, is equal to n square n naught. Here n naught is 52.9 picometer. Thus the radius of the first stationary state is called Bohr orbit, okay, the radii of the first stationary state, okay. So the first stationary state means n is equal to 1, okay. When n is equal to 1, this is the first shell or orbit, okay. So in hydrogen only one electron is there. Okay, so only one electron and only one orbit. Okay, that means for hydrogen n will be equal to 1, and then for hydrogen radius will be, the radius of the stationary state will be 52.9 picometer. Okay, so this radius will also depend on the number of shell present. Okay, if n is equal to 2, then this value will change. Next, the energy of each stationary state is given by the expression. Okay, so each orbit has its energy. Okay, that's why, okay, after with the passage of time, okay, the energy of the electron in that orbit does not change, and since its energy does not change, it does not collide with the nucleus. Okay, it does not lose its energy. Okay, however, it may jump from one state n1 to n2, okay, or n1 to n3 like that. So the energy of its stationary state is given by En is equal to minus RH 1 by n square, and then n is the integral value. Okay, so where RH is Rydberg constant and its value is 2.18 into 10 to the power minus 18 joule. Okay, so this minus signs comes. Okay, so there is attraction between the nucleus and the electrons. Okay, so we know that the electrons, okay, is charged particles, and also after absorbing energy, okay, it loses energy also. So it loses energy. Okay, there is attraction between them. Okay, so higher the charge here, okay, more attraction between the electron and the nucleus. Okay, I mean higher the positive charge. Okay, so electrons, okay, will after absorbing radiation will lose energy. Okay, so since they lose energy, minus signs comes here. So the energy of the first stationary state, okay, or is given by E1. Okay, E1 means the n is equal to 1. Okay, when n is equal to 1, so 1. Okay, so the value will be same. Okay, we'll get the same value, 1 by 1 square, same value. Okay, so energy of the stationary state n2, where n, when n is equal to 2, so this value comes here and then 2 square, and then what we get is 0.545 into 10 to the power 18 joule. For n is equal to this omega, gamma, this also means that infinity. Okay, this symbol also means infinity, or when the electron is very far away from the nucleus. So when the electron is far away from the nucleus, okay, we will see no attraction, okay, between the nucleus and the electrons. Okay, so there won't be any energy, okay, between the nucleus and the electron, so energy will be 0. Bohr's theory is also applicable to the ions containing 1 electrons. So those ions which contains 1 electrons, okay, they also this theory is also applicable to those, okay, ions. Example, helium H plus. Okay, so helium has 2 proton and 2 electron. Okay, so if we remove one, only 1 electron remains. Okay, likewise helium also, if you remove 2 electrons, 2 plus means 2 electron removed, 1 remains, and then beryllium also like that. Okay, so in this case the formula slightly changes. Okay, the energy of the stationary state will be minus 2.18 into 10 to the power 18 z square by n square joule. So z square is the atomic number. Okay, so for hydrogen the atomic number is 1, but here, okay, helium atomic number will be 2. Okay, and likewise the value for this lithium beryllium, okay, will change. And radii, the expression also slightly changes. Okay, Rn is equal to n square n naught by atomic number. Okay, since for hydrogen atomic number is 1, hydrogen will give the same value. Okay, n square by n naught, okay, into pm picometer. Okay, so what you will get is 5.9 n square by z picometer. It can also be, okay, through this model, okay, velocity can also be calculated for electron. However, it is not being given in your text also how to calculate, but roughly, okay, velocity of electron increases with increase of charge. I've written this in short form: charge, okay, positive charge represented by Q on the nucleus. Okay, so when this positive charge is contributed by proton, okay, proton in the nucleus. So as the number of proton increases, there is attractive force between the electron and the nucleus, so electron will move much closer toward the nucleus. Okay, and the size will decrease. Okay, the size of the atom will decrease. Okay, so it will move faster, and therefore velocity will also increase. Okay, and decrease when the increase of principal quantum number. So principal quantum number means n. It's okay, means 1 2 3 1. This means number of shell. Okay, so this shell increases. Okay, the electron move farther away from the nucleus. Okay, so if electron move farther away from the nucleus, there will be less attractive force, and therefore velocity will decrease. So for this case also, okay, only one electron remains. Okay, but the number of protons will not change. Okay, so for these elements, okay, they have higher number of protons, so for this case the velocity will be higher. So next topic is explanation of line spectrum of hydrogen. So Bohr was able to explain, okay, the line spectrum of hydrogen quantitatively. So this line spectrum of hydrogen we have discussed earlier also, like those Balmer series, Brackett series and all. Okay, Van series, okay, those. Okay, so he was able to explain this quantitatively. So suppose an electron, okay, an electron after absorbing radiations, okay, will move from ground state to higher state. Okay, and we call it as transition also, from ground state to higher state, or we let's say initials to final state. Okay, and after absorbing radiation they move to higher state, and then after what will happen is after some time they will lose energy or radiation and come back to the original or initial state. Okay, so in this case what happens is absorption of radiation and then emission of radiations take place. Okay, so the energy gap, okay, between these two orbits, okay, this and this orbit, is given by delta E. Okay, energy delta E. So we use delta for smaller value. Okay, E final, E initial. So final minus initial will give delta E. So we have already discussed, okay, the energy of stationary state is given by E n, okay, minus R h, okay, 1 by n square. So n can have value this. So by combining these two equations, okay, what we'll get is delta E is equal to minus RH by NF square minus RH by N initial square. So here Ni and Nf, okay, are so here Ni and Nf are the initial and final orbits. So further simplifications of these equations, okay, taking RH as common, okay, RH. So this will get this value, and we know the value of RH, okay, 2.18 into 10 to the power minus 18 Joule, 1 by Ni square minus 1 by Nf square. So this value, okay, using this value we can find out the energy gap, okay, between the final orbit and initial orbit, okay. So if you are to find the energy gap between these two, okay, final orbit and initial orbit, you will use this, okay, relation to calculate. So if you are to calculate the frequency, okay, so the frequency, if you are to calculate the frequency, okay, previously we have discussed about this also, delta E by H, okay, given by delta E by H. So delta E, this relation, okay, RH H, okay, 1 by Ni square is 1 by Nf. So this value, okay, here we got this value, and H is Planck constant, okay, we'll put the value of RH and Planck constant and calculate. So this, we got this value 2.18, okay, Joule. Planck constant 6.626 into 10 to the power minus 34 Joule second, and I square 1 by Nf square. So after calculations, what you will get is 3.29 to 10 to the power 15, okay, 1 by Ni square and 1 by Nf square hertz. So frequency, the unit is hertz, so we are writing in hertz. So this second will change to second inverse, okay, if you calculate. So this second inverse is simply means hertz, okay. Now if you are to calculate in terms of wave number, okay, so this relation, okay, this relation, or we will use this for calculation of frequency. And now for wave number, okay. So wave number is given by, okay, nu by c. So this frequency value we got, okay. So how this value is coming, okay, since we know lambda is equal to c by v, okay, and this wave number is equal to 1 by lambda. So lambda we got, so this will invert, okay, so inverse of this, okay, and then this value comes as nu by c, and c here is the speed of light. So what we will get, okay, after putting the values, RH value we got as 3.29 into 10 to the power 15, okay. We'll put this value and divide by the value of light. This will be NF, and the final value will be 1.09677 into 10 to the power 7. So wave number, okay, you will use this value to calculate the wave number, okay. And then this value is similar with the Rydberg constant in the line spectrum of hydrogen atom, okay. We have discussed that one. This value is similar with the Rydberg constant, okay, in the line spectrum of hydrogen atom. So he was able to give the quantitative value, okay, of spectral line of hydrogen. Now limitations. It fails to account for the finer details of doublet, that is to closely space lines of hydrogen atom spectrum observed in, okay, observed through spectroscopy. Different space lines, okay, observed in the spectrum of hydrogen, okay. These lines, okay, he was unable to explain, okay, why these closely spaced lines were observed in the hydrogen atom, okay. This model was also unable to explain the spectrum of atom, okay, other than hydrogen or hydrogen like ions, okay, which contain 1 electrons, okay. This model failed to explain that. However, this model was able to explain the stability and spectral lines, okay, of hydrogen like ions such as He plus, Li2 plus, okay, Be3 plus, okay. It was able to explain the stability and spectral lines of these okay, contain one electrons, but it could not explain helium, okay, which contain two electrons. Okay, so this theory failed to explain, okay, those elements having more than one electrons, okay, the spectrum of those elements. Further, it was unable to explain the splitting of spectral lines, okay, in the presence of magnetic field known as Zeeman effect or an electric field known as Stark effect. So a spectral line, okay, in presence of magnetic field, okay, split, okay, in discrete or specific lines, okay. So why this happens, okay, this model could not explain, okay. Likewise, in presence of electric field also, okay, it gives this splitting of spectral lines takes place in discrete or specific lines, okay. So this theory again failed to explain it. It could not explain the stability of atoms, okay, to form molecules by chemical bonds. So this theory could not explain the how atoms form, okay, molecules. An electron is regarded as charged particle, okay, charged particle written in short form, okay, moving in well-defined orbits. So this model, okay, has taken into account, okay, that electron is a charged particle, but the wave nature was not considered. So this charged particle, okay, has both particle nature and wave nature, okay. So wave nature was not explained here. Further, an orbit is clearly defined path, okay. So orbit has a clearly defined path, and this path, okay, must have position and velocity, okay. This orbit must have a defined position and velocity, okay. Of the electron are known exactly at the same time, okay. So if this orbit has a well-defined path, okay, this path must be completely, okay, be defined, okay, only if both the position and velocity of the electron are known at the same time. So both this path can be defined, okay, when the position and the velocity of the electrons are known. However, it is not so, okay. It is given by Heisenberg as an uncertainty principle, okay. This is not possible according to uncertainty principles, okay. It is not possible to define the exact position and the velocity of electrons, okay. So we'll discuss that further about the uncertainty principle in the next class, tutorial class. So this theory, Bohr model of theory, okay, it is too simple, okay, too simple. And then after this, okay, we'll discuss about the quantum mechanical theory, okay.